Hi, today we are going to be looking at concavity. For this, we're going to say let our function f be differentiable on an open interval a comma b, and we're going to be taking our second derivative of it. So if a second derivative of our function is greater than 0 for all of x on our interval a comma b, then our function f of x is concave up on a comma b. If that second derivative, so f double prime x, is less than 0 for all of x on a comma b, then f of x is concave down on a comma b. So for example, if we had this as our graph, f double prime of x, or our second derivative, would be greater than 0. Because essentially, our second derivative is how our slope is changing. So if our slope is changing to a positive, it's becoming less and less negative and eventually positive. So we can say from this that f prime of x, which would be our slope, is increasing at all times. Because we can see that we had a fairly negative slope, it becomes less and less negative, and then becomes positive and increases and becomes steeper and steeper. If this is our graph, we can say that, actually I should also mention with this one would be concave up. Where if this is our graph, f double prime, or a second derivative of x, is going to be less than 0 or negative. F prime of x is decreasing because we start out with a positive slope and it becomes less and less until it becomes negative. Now we can say f of x is concave down. Okay, so that will also brings us to what's known as a point of inflection. If our function f is continuous on an open interval that contains c, if f double prime x changes from its sign from positive to negative or negative to positive at x equals c, then f of x has a point of inflection at x equals c. So I've drawn out a few points where we have, or graphs where we have inflection points. So this point here, which would be C, this point here would be an inflection point. So on the left side of it, f double prime of x, in this case, is greater than 0. And on the right side, f double prime of x is less than 0. And right at C, f double prime of x is equal to 0. This one would have something similar. So we've got our inflection point at this location. To the left of it, we can see that our graph had a positive slope. It becomes less and less and becomes negative. So therefore, f double prime of x is less than 0. Where on this side of it, our graph has a slope that starts becoming positive. So f double prime of x is greater than 0. And this one also has f double prime of x, or a second derivative of x, at c. So yeah, I should actually replace these with c's. F double prime of x at c equals 0. Now this one also has an inflection point. And to the left of it, we can see our slope is getting steeper and steeper in a negative direction. So we can say f double prime of x is less than 0. To the right, we can see it gets steeper and steeper in a positive direction. So we can say greater than 0. But we can see that our graph is not smooth at this location, and f double prime x, or sorry, of c is undefined at this point because that's not going to be differentiable. So for example, let f be the function f of x equals x cubed minus 3x squared plus 4x minus 5. We're going to find all intervals on which the function is concave up or down and find the coordinates of the point of inflection. Okay, so first thing we're going to do is take our first derivative, and then we'll take our second derivative. So if we have f prime of x, that's going to be 3x squared minus 6x plus 4. Our second derivative, or f double prime x, is going to be 6x minus 6. And we can see that f double prime x is going to equal 0 at x equals 1. So just like in the last section of notes, we're going to rely a bit on line graphs. So in this case, we only have one point that we're very concerned about, and that has an x value of 1. So we're going to figure out whether f double prime x is positive or negative in each of the segments that this has split our line graph into. So if we have f double prime, our second derivative of x, and we want to choose a point on one side of this, I might say try 0. So we're going to have f double prime of 0 is equal to 6 times 0 minus 6, so that gives us negative 6. So we can see on this side it's going to be negative. And then if we have f double prime of this side, so I'd say 2 of 6 times 2 minus 6, that gives me positive 6. So that's a positive value, so we can see it's positive on this side. Now, we can see that on this side, our f double prime was negative. So that means that this side is going to be concave down. This side was positive, so we can say that that side is concave up for x is greater than 1. Now we want it for point of inflection. We know the x value of our inflection point, which is 1. We don't have the y value of it yet, though. So therefore, we'll just go back to original function and substitute in 1. So we've got f of 1 is equal to 1 cubed minus 3 times 1 squared plus 4 times 1 minus 5. And that gives us negative 3. So we can say our point of inflection is at 1 comma -3. Okay, next example, the cubic function y equals ax cubed minus 3x squared plus bx plus c has a point of inflection at a point 1 comma 6 and a relative maximum at x equals -1. We want to find our values of a, b, and c. Okay, so first thing I'm going to start by doing is taking the derivative of this function. Now I'm going to swap out, actually before taking the derivative function, we can substitute our 1 comma 6 in here to get a relationship between our a, b, and c. After that, we'll take our first derivative of this function. And then because we know where we have a relative maximum, we know where our first derivative should equal 0, and that will also give us an equation that involves our other variables. And then we'll take our second derivative and use it at our point of inflection to solve for more. Okay, so I'm going to swap out y with f of x. So we know that we have an inflection point at 1 comma 6. So therefore we know that if we have this original function, which like I said, I'm just going to swap out for y with f of x. So our original function was f of x equals ax cubed minus 3x squared plus bx plus c. And we know we have an inflection point that is 6 comma 1. So we know 6 is equal to a times 1 cubed minus 3 times 1 squared plus b times 1 plus c. So this simplifies down to 6 is equal to a minus 3 plus b plus c. Moving the 3 to our side, we've got 9 is equal to a plus b plus c. Now we're going to look at our first derivative. So our first derivative of our function is going to be 3a x squared minus 6x plus b, and derivative of constant term is going to be 0, so our c does not continue on with this one. Now, if we have a relative maximum at -1, we know the slope at that location is going to be 0. So we know f prime of x at -1 is going to be equal to 0. So we can go 0 is equal to 3 times a times -1 squared minus 6 times -1 plus b. So we have 0 is equal to 3a plus 6 plus b. I'd probably move the 6 to the other side, so we've got -6 is equal to 3a plus b. So we're still not able to solve for one of our variables, but we've managed to eliminate one. Next, we're going to get our second derivative. So that's going to work out to 6ax minus 6. Now, if we have an inflection point at 1 comma 6, that means our double prime of f, or our second derivative of f, at 1 is equal to 0. So we know that 0 is equal to 6 times a times 1 minus 6. Now moving this 6 to the other side, we get 6 equals 6a. So we know that when we divide both sides by 6, 1 is our a value. So we already now know our a value. We can then substitute that back into this equation. So we've got negative 6 equals 3 times 1 plus b. So we've got negative 6 equals 3 plus b. Move the 3 to the other side, so negative 9 equals b. So we now know our b value. Now we can go back to this original equation. We know our a and our b, so we know we've got 9 is equal to our a, which is 1, plus b, which is negative 9, plus c. So we've got 9 is equal to negative 8, plus c. Adding 8 to both sides gives us 17 equals c. So we have our c value. So down here, I would just put all the answers together. So a is equal to 1, b equals negative 9, c equals 17. Okay, so next we have our second derivative test. It states that if our first derivative at c equals 0 and our second derivative at c is less than 0, then f of x has a relative maximum at x equals c. And if our derivative of f at c equals 0 and our second derivative of f at c is greater than 0, then it's going to have a relative minimum at x equals c. So we'll do an example. So find all relative extreme values of our function. So we have f of x is equal to x cubed minus 12x plus 5. So first thing I will do is take our first derivative so that we can solve for locations of any extrema. So our derivative of x cubed is 3x squared, or our derivative of negative 12x is negative 12. Our derivative of 5 is just 0. Now, if we look at this, we can factor it. So we can factor 3 out, so that becomes 3 times x squared minus 4. We can recognize this as a difference of squares, so that gives us f prime of x, or derivative of f, is 3 times x plus 2 times x minus 2. So we can say that we have critical points at x equals negative 2 and positive 2. Now next we will get our second derivative. So we've got f double prime, or our second derivative of x, is equal to our derivative of this. So this would be 6x. And derivative of negative 12 is just 0. So we've got f double prime of 6x. So at this point, we're going to find f double prime of negative 2 is equal to 6 times negative 2. So that gives us negative 12. So based off of this being negative, that means that this is going to be a relative maximum. Or if we have f double prime of positive 2, that's going to give us 6 times 2. And because that gives us a positive number, that's going to give us a relative minimum. Now we probably want our exact locations of these. So if I have f of negative 2, I'll substitute that into here. So that gives us negative 2 cubed minus 12 times negative 2 plus 5, which gives us 21. And if we have f of 2 cubed minus 12 times 2 plus 5, that gives us negative 11. So as expected, our relative maximum is a larger number than our relative minimum. So we can say we have a relative maximum at negative 2, comma 21, and we have a relative minimum at 2, comma negative 11.